Thanks a lot for the invitation. Of course, we probably would all prefer to be now in India and not sit at home, even though my background may be kind of funny. I don't know what you see. But anyway, really, thanks a lot for organizing this precursor, and it's fantastic talks. It's really great to see, our fellows, colleagues, and friends, and it's really great. So I changed the title because I thought that to have Yifu and Masahide, it's enough for the bounds. And therefore I decided to tell you about something more crazy than the bounds. Okay, so let me go just to my main message. And my main message is the following. It contains a couple of points. So point number one, so there are local field theories, these actions which look quite normal. And in this local field series, there can be dynamical degrees of freedom which are actually global. And well, how can we understand the global degree of freedom? For example, it can be given by an integral over whole Cauchy hypersurface. Okay, so that's quite a funny situation which I would not expect to see in a very simple action. Then why these degrees of freedom are interesting? The point is that they can actually mimic free parameters in the usual action. So in particular, in the GR action, both the cosmological constant and the Newton constant, and Newton constant gives us Planck scale, right? They both can be such global degrees of freedom. Interestingly enough, even though they're global constants, if you want, for all classical purposes, they will remain constants, still they are subject to quantum fluctuations. And the origin of the values of these global degrees of freedom, of these constants, if you want, should be then in quantum cosmology. So in some sense, our constants in, let's say, Einstein-Hilbert action plus cosmological constant, so both these dimensionful constants are actually results of some quantum cosmology and the Big Bang. Another interesting ideological thing is that allowing for constants to be arbitrary, and or if you want to be given by your some initial quantum state, introduces you an ideal landscape. So basically, without any string theory, without anything, you can think that there was a distribution of these parameters. Okay, so now basically you know everything what I want to tell you, and I can go into more details. And to begin with, let me remind you what you all know, namely that if you try to calculate vacuum energy, we are in trouble. Of course, how would we calculate vacuum energy? Well, the usual story, we sum up zero energies for each mode, and each mode is an oscillator, so we know how zero energy looks like. So it's h omega by half. All other terms will be proportional to coupling constants. And if we are in weakly coupled regime, then these terms are supposed to be small. Then we know that if we're dealing with Lorentz invariant systems, then the T-mu which is produced should be just proportional to this lambda. And then, as actually it's very nicely explained in the review by Jerome, you need to do something with this integral over k, and this integral has to be regularized in a non-trivial fashion. And one can guess why it is the case already from the very simple perspective that integral for pressure, part of this energy momentum tensor, looks very, very similar. And of course, by naive straight calculation, it would be always positive, because that's normal weakly coupled field theory. and it would not provide you negative pressure. However, if you do things correctly, then the pressure would be negative because you need to reproduce lambda. And that's purely the artifact of regularization, renormalization, and Lorentz invariance in post. Okay, but anyway, doesn't matter how we estimate it, as far as we just need to write some dimensionful parameter. And some people claim it should be mass of the heaviest particle to the 4. Some others claim that it should be just cutoff to the 4. It's not very relevant because observation tell us that lambda is 10 minus 29 grams per centimeter cube. And actually that implies that it's roughly speaking 10 minus 3 electron volt power 4, 10 minus 9 of the masses of electron power 4, 10 minus 15 of the energy which we have already probed on LHC. So basically, it's very hard to imagine that the situation here would be solved through some effective field theory or something just because of the scales which we are dealing with. And that poses a very straight question, namely, should vacuum really have any weight or not? So, and surprisingly enough, this question was partially answered by, or at least addressed by Einstein more than 100 years ago, actually 101 years ago. And the way to go is to lose the trace. Okay, so if you get lost, then you may solve something. So that's a kind of funny situation. So basically, you need to study traceless Einstein equations. Okay, so let's see how does it work. So instead of usual Einstein equations, I use Planck units. So therefore, 8 pi g Newton is equal 1. So you should forget these equations. And instead of them, you write actually only trace-free part of these equations. Sounds like a bizarre modification of normal equations of motion. It's like really order 1 modification. However, if you use Bianchi identity and energy momentum conservation, then you see that applying covariant derivative, you just get conditions that the difference between traces of the Einstein tensor and the energy momentum tensor is always a constant. So now basically you declare that the constant of integration which you obtain out of this differential consequence is lambda, and you plug it in back and you obtain normal Einstein equations with a cosmological constant which is now arbitrary. So basically you kill the role of lambda to be a constant of the universe to just integration constant, even though of the universe. And this is their article of Einstein where he introduced it. It's actually very nicely written, and he discusses why should it be the case. So basically here, unfortunately, I don't have a pointer. So here you can see that there is 1/4 and not 1/2 as one would expect in this equation. Okay, so basically the point is, why these equations are funny? Because if you look at the structure, they are completely ambivalent with respect to any shifts which correspond to vacuum energy momentum tensor. So basically, if I take T mu and add to T mu lambda mu, these equations don't care because they don't feel the trace, which is kind of nice property. And of course, people then discuss whether it's proper procedure. So basically, at which moment are you supposed to fix this constant of integration? Before dealing with the vacuum or after that, and so on. But to my mind, these are the original equations, so therefore you are going to fix the constant after that. So therefore, it looks like they're really symmetric with respect to such shifts. Okay, so surprisingly enough, this type of formulation of the Einstein theory of relativity is actually known under the name unimodular gravity. So why it is the case? So now I'm going to tell you something kind of standard for first year or second year of the university, and not standard for normal talks. So, namely, we can go back, forget everything what we know about normal integral variational principles of mechanics, and go to D'Alembert principle, or if you want, differential variational principle of mechanics, and look at Lagrange equations of the first kind. So, namely, we go just to normal Newtonian mechanics. So we have different particles, they're labeled by I. So we have acceleration A, we have the force F acting on each of these particles, and we have so-called virtual displacements, delta R, for each of these particles. And then the statement is, for normal ideal constraints, basically, which are given by this formula, right? The first equation would be your dynamical equation, in a sense that you allow arbitrary virtual displacements which are compatible with the constraint, and you need to satisfy the first equation. So if you want, basically it just tells you that the reaction forces due to these constraints don't perform any work. Okay, so the funny thing is that as a consequence of that, you immediately obtain that if you want, these two equations are roughly speaking symmetric. Actually, the constraint can even depend on acceleration if you want it, even though it would kind of be not a nice equation from the point of view of well-posedness and so on. But anyway, the point is that out of these two conditions, you can get that only the sum of them with arbitrary coefficients should be 0. And that's why what you get is the force due to the constraint, which is just Lagrange multiplier acting on the constraint. And this Lagrange multiplier is, of course, an arbitrary function. And this expression is usually called Lagrange equation of the first kind. And the funny thing is here that you can get rid of this Lagrange multiplier just by, let's say, you multiply with the same constraint, okay? And then plug it in back and write it in this way. Okay, so now the point is we can follow this strategy and try to see what is the kind of variational principle which would provide you this so-called unimodular gravity. And it's actually very easy. So the analog of this so-called main equation of constraint dynamics, you get just normal Einstein equations multiplied with virtual displacements of the metric. And then you have the constraints, the J mu multiplied with this virtual displacement of the same metric as 0. And of course, the result is exactly the same first kind Lagrange equation of the first kind, which now creates as a Lagrange multiplier this cosmological constant lambda. And of course, similar to the just procedure above, you can exclude this Lagrange multiplier by multiplying it with the metric. And if you do that, you obtain traceless Einstein equations, which also makes sense because you want, out of the variational procedure, you want to obtain something which is expressed purely in terms of things you were dealing with, and not some unknown reaction forces. Funny, you know, that you can also rewrite it in different ways, which are less nice, but still interesting. And for that, you need to assume, for example, that either the Einstein tensor is not vanishing and its trace, so that you can write this, or T mu is not vanishing along with the trace. In that case, you can write this. As you see, all these equations don't have any cosmological constants there, so it will appear purely as a result of integration of Bianchi.
ହଠାତ୍ ରାଗି ଯାଉଛନ୍ତି ତାଙ୍କର ଟିକେ ଯେ ବ୍ୟତିକ୍ରମରେ ପଇସା ମାନେ ଜିନିଷ ମିଳିଗଲା ପରେ ସେଟା ରାଗି ଯାଉଛନ୍ତି ସେଟା ବର୍ତ୍ତମାନ ଖରାପ ଗୁଣ ଶାନ୍ତ ଯେତିକି
Okay, so basically now you have seen how it works for unimodular gravity, but the key point is that all these equations are per construction actually generally covariant, and in this differential formulation, as differential constraint is also general covariant because it's just the metric, so the whole thing is generally covariant. However, what is a funny thing happening here is that if you integrate this constraint, that gives you a non-covariant, so-called unimodular condition, apparently non-covariant, because it basically states that the square root of the metric is just some arbitrary, not fixed, not specified, not dynamical function, which is of course a very weird situation, and that actually forced many or people to say that this function is just, let's say, 1, okay? Which is of course ridiculous, because in that case you would not be able even to use spherical coordinates. And it causes a lot of confusion, this issue in this community. And of course the point is, we know that all these equations are generally covariant. They're different variant, no problem. So the equation would be how to formulate an action principle, so an integral variational principle, right? To actually avoid this non-dynamical function, to make it dynamical. And because now it will be dynamical, we need to kind of make it irrelevant. So that already implies that there should be some gauge freedom. Okay, and that was achieved long time ago by actually Henneaux-Teitelboim. And you can think that this action is just action for all de Sitter and anti-de Sitter spaces simultaneously. Because, and as you see, it's a very, very, very easy action. So your dynamical variables is the metric, this vector field W, and this scalar lambda. And this action has some really funny properties. So of course, it's trivial to check that if you vary it with respect to the metric and the fields, then on equations of motion, the energy momentum tensor is exactly cosmological constant. But then the properties are the following. First of all, you have a gauge degeneracy with respect to shifts, and the vector that you use to shift is actually divergenceless. And you see that already makes out of the constraint in this section, what you obtain is that the square root of the metric is given by this derivative of the square root of this, if you want, vector density. And now this W is dynamical, but it's degenerate with respect to the gauge transformations above. So therefore, it's not observable. Then, funny enough, you know, you wanted to restore gauge invariance, namely different variance, but the price for that to pay was that actually you introduce kind of fake violation of Lorentz symmetry, because of course this W mu can never be 0. Nevertheless, of course, on the level of equations of motion, it doesn't play any role at all. Moreover, this W mu is not observable because it's gauge dependent. So another thing is that the density of the cosmological constant in this de Sitter or anti-de Sitter space is actually a Lagrange multiplier. And then if you look at the structure of this action, there is only one time derivative, right? And the action is linear in this time derivative, so therefore it's actually first order action. And if you, basically it's in the form P Q dot minus H. And if you look at this, then you immediately realize that exactly as Professor Yamaguchi was discussing and some other guys, there is basically in Ostrogradsky Hamiltonian, there is this problem that it is linear in momentum. So indeed, this system is also linear in canonical momentum because your canonical momentum is just proportional to lambda. But the point is, on all equations of motion, the derivative of this lambda is just 0. So therefore, there is no way to abuse this channel of instability. So basically, this system is stable. Okay, so another thing is that, of course, there is no dimension full constant. So therefore, it's actually a scale invariant system. Okay, so now let's go a bit further. So if you look a bit more precisely, the point that the special gradients of lambda correspond to 0, they vanish identically, that is that this is constraint. I can usually plug in constraints following, let's say, Faddeev-Jacqueff back into the action. And if I do that, then I realize that, okay, in this first order action, I can move the special integral behind lambda, because lambda does not depend on space. And that would imply that the actual quantity conjugated to lambda is not W, is this integral below. And it's quite a funny situation, because if you look at the physical meaning of this integral, then first thing we can notice is that due to the gauge symmetry, this integral gets shifts. So it's basically shift symmetric coordinate. And we know, of course, that if you have shift symmetric coordinates, then momentum is conserved from mechanics. On the other hand, if you just take a derivative of this quantity, then due to this constraint, or if you want, due to this production of this would-be current W, if you neglect, if you have proper boundary condition and you can neglect special components of this vector on special boundary, on special infinity, let's say, then the only term which remains is basically the volume, the full volume between two Cauchy hypersurfaces. So that's the quantity which remains, of course, invariant. So basically, the physical meaning is this, the whole space-time volume between two Cauchy hypersurfaces, of course, supplemented with some proper boundary conditions. So that's I have already explained you. But of course, what is important, so there is quantum mechanics is unavoidable. So if we write some action and we know that it's already in Hamiltonian form, we know what are the conjugated quantities. If quantities are conjugated, then there is unavoidably Heisenberg-uncertainty relation. And this Heisenberg-uncertainty relation tells us that basically the quantum fluctuation of this full volume between two Cauchy hypersurfaces multiplied with the quantum fluctuation of cosmological constant should be always larger than h bar by half. Okay. By the way, how much time do I have?
So you have 7 minutes?
Ah, okay, perfect. Thanks. So now another point is that this W mu is a rather unusual field. You know, for particle physicists, that sounds very ridiculous to have such a vector field. And of course, we would all prefer to have a gauge potential or connection, let's say for some SUN, to do the job. In particular, because that would allow us to see whether such action can be embedded in something more usual, more similar to normal stuff which we have, let's say, in standard model. And you see, that was our motivation with my students, Katrin Hammer and Pavel Jerushek. And so basically our idea was the following. So we decided that one can use Chern-Simons current instead of this vector. And basically after that, that provides you an action which looks very nice, because there are Lagrange multiplier now enforces the constraint that f of dual should be equal to 1. Of course, you can always introduce proper dimensions if you want there. And the funny thing is that, of course, looking at the structure of this action, we see that lambda plays exactly the same role as an axion. So that's what we called axionic cosmological constant. And how we decided to use the Chern-Simons term, which looks like this for general non-abelian field theory, is different points were contributing to that. So first of all, we realize that in this, so it's a composite vector variable. So actually it's a complicated change of dynamical variables. But remember that for us, as a real dynamical degree of freedom was only important this integral of the time component. But for this Chern-Simons, the time component never has derivatives of this vector A mu, of our gauge potential. So Therefore, it implies that by doing this change, we don't change number of degrees of freedom in our action. And that's good. So just to remind you that basically the divergence of this current is given by FF dual defined as usual. And the point is that gauge transformations would actually introduce exactly the shifts which we needed. So that's a nice property. And then we of course checked that this action exactly reproduces the unimodular structure. So interestingly enough, there was an old paper by David Finkelstein, is the guy who introduced Finkelstein coordinates. And in '71, he brought a paper basically reviving Einstein traceless equations. And basically he was saying that probably some nuclear physics or atomic physics at that time would provide the scale to kind of introduce this unimodular lambda, to provide you, if you want, full volume element. And maybe the scale which corresponds to it is some confinement scale, I don't know, some Young-Mills theory, maybe even QCD. That's too brave maybe, but it's interesting. Because you see, this FF dual really provides us an alternative for volume measure, if you want. Okay, another thing was that it was also speculated by Frank Wilczek that one can do for lambda the same thing as for theta in QCD. And another thing was that Tony Patil in 2012 was also discussing such models, but from a very different perspective, because he wanted that lambda is not generated by quantum corrections. Okay, now let me very briefly say what is the second way to lose a trace. And that's actually the real point of this talk, the novelty, so to say. So let's have 1 equal 1 instead of 0 equals 0, okay? It's still as tautological as 0 equals 0. So how can we lose a trace of Einstein equations in a different way? So let's write this. And that's actually, I thought we are going to put it on archive before this nice conference, but I think it will take whatever, 2-3 days more. So the point is, let's divide each side of the Einstein equation by its own trace. It looks bizarre. Of course, it requires that these traces do exist. But if we do that, then we perform exactly the same procedure which is outlined in the normal unimodular story. So we use Bianchi identity, we use energy momentum conservation, and here on top we need to assume that there is non-degeneracy of T mu, which can be always achieved if we think that T mu may contain an actually very, very small but fixed now lambda. So if we do that, then Bianchi identity will give us the conditions that actually d mu log g divided by t is equal to 0, and that implies that these two traces are again proportional and the coefficient of proportionality is just a constant. So basically we made M Planck to be merely an integration constant. And now we can go again to this D'Alembert principle, and here it's even more funny because instead of imposing a differential constraint metric, delta metric is equal to 0, we impose now T mu multiplied with their variation of the metric to be 0. And if you impose that, then you obtain through the same story of, if you want, first kind of Lagrange equation, you obtain lambda of x to be there as an arbitrary function, and then Bianchi identity would fix you that this function is actually not function but a constant. But more importantly, you can multiply this lambda by G mu nu, and you obtain exactly equations which I promised. So funny enough that G mu nu, delta G mu nu would also give you the same result. And following from here and taking analogy in their unimodular story and Henneaux-Teitelboim, we can write easily an action. Okay, so this action will look like this. So you write an action. It's again vector field. Now it's called C, and we have also alpha as a Lagrange multiplier. R is normal curvature. So the same thing. It's extremely similar to Henneaux-Teitelboim. So now there is a global shift symmetric degree of freedom, which is canonically conjugated to this alpha, and we understand that alpha plays the role of Planck constant. obviously, if you do the variations, then this alpha is constant on all equations of motion, basically on shell. So this global shift symmetric degree of freedom is given again by the same integral, though now it has slightly different meaning, namely instead of full volume between two Cauchy hypersurfaces, now it's integrated curvature between this, or Ricci scalar between two hypersurfaces. Again, if you forget about boundary conditions, then you immediately obtain this result. Okay, and now I'm converging because what is really funny, so for this integrated Ricci scalar, or if you want some variable which measures this integrated Ricci scalar between two given hypersurfaces, of course, because this quantity is conjugated to our Newton's constant, or if you want Planck scale or Planck mass, we obtain again a Heisenberg uncertainty relation. And now it's very interesting because, as you see, it forbids you from having an empty space. It forbids you from having a space without R. So basically, there should be always some quantum fluctuations in the Ricci scalar. Well, we kind of knew that it's supposed to be there, but nevertheless, you know, the amount of them is kind of non-local, and yeah, it's just straightforward manifestation of applying quantum mechanics to this global degrees of freedom. So actually, I'm done.
Okay. Thank you, Professor Vikman, for this nice talk. So I think I'll just go to the question and answer session. I can see a lot of questions for.
Okay. In that case, I see the chart. Perfect.
Okay. So the first question is by Devoprashad Maiti. So Devoprashad, will you please unmute yourself and ask your question? I can see you have two questions, so you can ask one after the other.
So the first question to Professor Jerome is it. So basically, you mentioned about the squeezing where you have the quadratic operators. Now, in the theory, if you have higher dimensional or interacting operator, three, say A dagger A, something like that, then this squeezing can be reduced because of the higher order term. Yeah, can you hear me?
It's slightly better now, yes.
Okay, so basically my question is, you talked about squeezing where in the Hamiltonian you have only quadratic operator.
Yes.
So but now if you consider the higher order operator, then does that higher order operator contribute to the squeezing, or can it reduce the squeezing or enhance the squeezing?
So by higher order operators, you mean something that could be cubic or quartic in the creation, and yeah. But in that case, it would no longer be the. It would no longer be a quadratic Hamiltonian. So I guess you want to consider a situation where you have where you expand the action. I don't know, to cubic action or quartic order or something like that.
Yes.
Yeah. But it's not clear how to answer your question, because in that case, the quantum state of the perturbation would no longer be a Gaussian state.
Okay. Yes. But we can.
Yes. Sorry.
So if we consider in the limit where like you have three momentum, but one momentum is very large, something like that we do in quantum in usual inflation. In a squeeze limit, we talk about non-Gaussianity. So here also, if I have three operator, and then one operator is essentially behaving like a classical.
Yeah. Yes. So if you consider non-Gaussianities, it means that you have cubic order operator in the action, and in that case, I think it's changed everything. For instance, at this order, I don't think the Wigner function would remain positive definite, because the quantum state of the perturbation will no longer be a Gaussian state, and it's known that the only state that leads to positive definite Wigner function are the Gaussian states. So if you have a quantum state which is no longer Gaussian, I guess the Wigner function could exhibit some non-negative behavior in some part of phase space. I don't know if this answers your question.
Yeah, so I just another question I wanted to ask. You mentioned about fictitious spin operator.
Yes.
So I mean, you have mentioned that that's fictitious. That those operators actually follow this usual spin algebra, and you
Yes.
can define, you can calculate the Bell inequality related to those operators. But
Yes.
how can you measure in the real sense? How can you measure?
So it's of course a very important question. So so maybe I can try to share my screen again. Can you see my slide?
Yes. Yes.
Yes. So for instance, if you want to measure, so let's discuss first the z component of the fictitious operator. So this operator, I don't know if you can see the pointer, but
Yes, I can see.
yeah. So this one. So the idea would be the following. You see, it's built out of this continuous Hermitian variable, and you can think of this Hermitian variable as the Fourier component of the curvature perturbation. So you could imagine you take the Planck map, and from the Planck map, by doing some manipulation, taking the inverse Fourier transform and so on, you can extract the value of the Fourier transform of the curvature perturbation for each mode.
Yes.
Yes. And so so this would be this would be a measurement of this quantity Q of K. And how can you measure the fictitious spin value? Well, you just divide the real line, which is the continuous spectrum of Q of K, into different cells of size L, and you give a label of to each cell, which is an integer, and according to the value at which you have found the QK, you attribute a value which is plus or minus 1, according to the value of the label of the cell in which it turns out that QK has landed. And this is how you could, so in practice, you take the map, you measure the Fourier component of curvature perturbation, and you attribute a value plus or minus 1, depending on whether the value that you have found is in a cell which has a even or odd label. So this is how you would do it in practice. Now, if you want to reconstruct a fictitious Bell operator, as you know, you need also to measure another spin component, because we need two non-commuting spin components in order to reconstruct the so-called Bell operator and to observe a violation of the Bell inequality. So this means that you would be obliged not only to measure the z component, which I think is possible, but another component, either the x component or the y component. I have not explained how you can define this one, but there are also concrete equations for the definition of the two other components. And here comes the problem, because I believe that in order to reproduce the procedure that I have sketched before for the z component, but this time for the x or the y component, you would be obliged to measure or to have access to the decaying mode of the perturbations. And so it's possible in principle, of course, but in practice, given the magnitude of this decaying mode, I think it's not realistic. It's not realistic to imagine that you can measure it. So by the way, this is also the reason why when people try to construct, I mean, I'm thinking in particular to the Maldacena paper about Bell experiment that was mentioned by Andy yesterday. This is why the model is so complicated, because at the end of the day, in fact, everything is made such that there is a situation where you can extract the decaying mode of the perturbations. And in standard vanilla inflation, you cannot do it. So you need a much more complicated model in order for the decaying mode to be accessible. And yes, so this is the main problem. You need two non-commuting measurement, and in vanilla models, I don't think it's possible to do it in practice, because the decaying mode is exponential -50, and I think it's lost forever. Does it answer the question?
Okay, yes, thank you.
You're welcome.
So the next question is also to Professor Martin. It is by Titas Matthew. So Titas, will you like to unmute yourself and ask the question?
Yeah, my question is maybe more general. That is the squeezing of perturbation modes playing the role of quantum to classical transition? It's a mere doubt.
So if you can still see my slides. So I would say no at the practical level, namely for the quantity that do not involve the decaying mode, such as a measurement of the power spectrum, bispectrum. In fact, whatever the value of the squeezing, you would always be, it will always be possible to reproduce the quantum averages by stochastic averages. Now, if you consider more tricky operators, such that the one I have given here, which involves the position and the momentum at the same time, or the spin operators that I have described before, then it's true that for these more complicated operators, you may need a large squeezing in order to re-establish the concordance between stochastic and quantum averages. You see it on this equation. The expectation value, stochastic expectation value of this observable is not equal to the quantum expectation value, because there is the -1, but the quantum expectation value is proportional to the exponential of the squeezing parameter. So very quickly, when R becomes large, this term will dominate over the -1, and then quantum and stochastic averages coincide. But this is true. So in principle, yes, you need the large squeezing. If you require the stochastic and the quantum averages to coincide for any observable, it is true. But if you now consider the observable, only the observable to which we have access, namely power spectrum, bispectrum, and so on, then this is true regardless of the value of R.
Thank you. Thank you for your detailed reply. Thank you.
You're welcome.
Okay, so now the next question is also to Professor Martin. So it is from Arsalan Adil. So will you like to unmute yourself and ask the question?
Yes. Hi. Maybe this point was made and I've missed it. There's this point made regarding the black body of the cosmic microwave background.
Yes.
And is the squeezing necessary for the CMB to be a black body? I mean, that just comes about by just evolving the Boltzmann equation, or do you mean that there's deviations from the black body spectrum point towards the squeezing?
No, sorry if it was confusing. No, the black body is about the background, and the squeezing is about the perturbation. So the squeezing is not has nothing to do with the black body. I was just trying to make an analogy between the fact that the CMB is the most accurate black body that we cannot reproduce in the lab, and the two-mode squeezed state of the perturbation is probably the strongly squeezed state ever observed in nature, and we are not able to reproduce it in the lab as well. But this was,
I see.
I mean,
I
just
see.
just an analogy.
Okay. Thanks.
Okay, so next question is by Swagat, but I think we can defer this question because this is a more common question and not related to the talk. So I'll now go to Saurav Pal's question to Professor Jerome Martin. Professor Saurav, can you just unmute yourself and ask the question?
Yeah. So my question is, in case of this fictitious operators, we have to take an ensemble average of the states or whatever that might be squeeze state. So how do we do that? Like here we can have a initial state of squeezed psi, then how do we make other like infinite numbers of states to make the measurements? Like, won't there be any collapse of wave function?
Of course, there is the question of the collapse of the wave function that I don't know how to answer. But I think the question was how do you measure the correlation function since they are ensemble average and we only have access to one measurement? Was it? I mean, did I understand correctly the question?
Yeah.
Yeah. So in that case, well, it's a question that goes beyond the measurement of these fictitious spin operators, and usually the answer to that is that you use some kind of ergodic principles, and you replace ensemble averages by spatial averages. So you divide your celestial sphere into various patches, and you I mean, since they were causally disconnected, you just say that a measurement in one patch and another measurement in another patch is the same as measuring twice the system. So yes, this is a kind of ergodic assumption. You identify, you make the identification between spatial averages and ensemble averages.
Okay, thank you.
Okay, so there's one question for Professor Vikman from Saurav Sur. Saurav, can you please just unmute yourself and ask the question? There's another question to Professor Vikman from Rose Bona. Can you please unmute yourself and ask the question? Rose?
Sure. Can you all hear me?
Yes, yes, please go ahead.
Hi, Dr. Vikman. I was just curious with your upcoming paper. Your approach seems fairly intuitive. Do you have any intuition why it hasn't been previously explored in the literature?
Good question. So actually, the literature there is pretty vast. You know, like it's very hard to overview it. So I cannot really promise you that somebody in let's say 30s has not done it. Just from the point that this modular stuff is 100 years old. Even though by very good people, you still find papers with square root of -1 to be equal to 1, to square root of -g to be equal to 1, and holds this confusion. So I don't know. I think everybody got confused from the point that what you need is the differential constraint, but if you try to integrate it, then you start breaking different variants. So I think that's what confused everybody. Regarding cosmological constant as constant of integration, the action was actually written in a similar form, at least, by Tony Padilla and Nemanja Kaloper and George Zachariade, I think. And they studied the sequester, and so basically they have a starting point, but to be honest, it was even hard for me to dig it up and to understand what they're doing. So what was not written to my best knowledge anywhere is basically how to approach this thing from losing the trace, to write exactly this 1 = 1. So that I have not seen anywhere, and I don't know. But with Tony, we discussed it. He also didn't know any other paper where basically the action for global Newton's constant would be written. So basically, he thinks that their work was the first when it was written. But their ideology is very different, and what they want is also very different.
Thank you for your thoughtful answer. I've also read the paper by Kaloper and Padilla, so that was very cool that you mentioned that. Thank you.
Cool.
So, okay, so we'll take one last question for Professor Jerome from Laura Iaconi. So Laura, can you unmute yourself and ask the question? And also Sharvari has the same question along the same line which she wants me to read. So Professor Jerome, can you hear me?
Yes.
So, okay, so I can read Sharwari's question and then Laura can ask her question. So Sharwari has asked, related to Laura's question above, if the wave function W obeys classical equation of motion because we treat perturbations linearly, then do quantum effects become apparent at second or higher order? I think you have partially answered to that question, or at perturbation at higher order should consider quantum corrections.
Yeah, so W is not the wave function, it's the Wigner function, right?
Is the Wigner function should be.
Yeah. Yeah, in principle, I mean, it depends which criterion you take into account, but in principle, if you take the argument that the system is classical because only if the Wigner function is positive definite, it's clear that if you go at the next order, I believe, also I have not done the calculation, but I believe that the Wigner function will no longer be positive definite because there is a theorem, again, I repeat, which states that the only state for which the Wigner function is always positive are Gaussian states. And I think it's clear that if you take into account the I mean, if you go to next order in perturbation theory, there is no reason for the state to remain Gaussian, and therefore, I think this will directly imply that the Wigner function will no longer be positive definite in that case.
Okay, and Laura, can you please ask the question?
Yeah, I'm here. So first of all, thank you very much for your talk. If
You're
possible,
welcome.
I would like to ask you if you could elaborate more on the possibility of measuring the quantum nature of cosmological perturbations. So I'm referring to the last slides.
Yes. So just to recap, I think in principle, it's possible to see the quantum nature of the perturbations. There was this claim that even in principle, it's not possible, but I think it's possible because even if the Wigner function of the system is positive, there is still operators for which quantum averages do not coincide with stochastic averages. So in principle, there is still the possibility to see a direct signature of the quantum origin of the perturbations. Now, I believe that in practice, this is extremely difficult. So for instance, if you try to construct this Bell inequality using the fictitious spin operators, also again, in principle, there is a violation of the Bell inequality, which signals the quantum behavior. In practice, it will be impossible to measure it. Again, it's always the same reason. It's because you need to measure two non-commuting operator, and one can be determined only by the growing mode of the perturbation, but the other is necessarily dependent on the decaying mode. And since you don't have access to the decaying mode, you will never be able in practice to observe the violation of the Bell inequality. So the only way out that I can see to this result is to design a situation where you measure only the Z component of the fictitious spin operator, because this is the only one which does not depend on the decaying mode, which involves only the growing mode of the perturbations. And the only way I see, if you work only with one component, is to replace a measurement at different spatial location by a measurement at different time location. And this leads to this Legette-Gark inequality, where you measure only one spin component, contrary to the Bell inequality, but the price to pay is that you measure it at different time. So in the context of cosmology, this would mean measuring only the Z component, but at different redshift. So it would be like doing the tomography. Maybe this would require the tomography of the power spectrum or something like that. This is the only way out I see in order to design a situation where concretely you can see a signature of the quantum origin of the perturbation. So, I mean, at the end of the day, either this way how it works, and this is great because you have a direct signature of the quantum origin of the perturbation, or it does not work. And then I think it's a kind of quantum censorship theorem that states that the quantum origin of the perturbation is hidden forever. But the only way I see for the future is this thing.
Do you
Okay,
think this is the? Sorry, can I ask another question?
Be very brief.
Yeah, super quick.
Yeah.
So do you think that doing this tomography is like something realistic that might be doable? Or not?
Yeah, I think people, there are two questions. I think doing tomography, I think people are going to try to do it in the future. I think Euclid will try to do tomography, I think, if I am not mistaken, try to do tomography of the perturbations. So this is one point. The second point is whether this will meet all the requirement of accuracy and so on to be able to check the Leggett-Gark inequality if we can solve the conceptual problems that are behind it. This I don't know.
Thank you very much.
You're welcome.
Okay, so let's close this session by thanking both the speakers for very nice talks, and also I'd like to thank all the participants for actively participating in the discussion session.